Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to start a new section of this unit first of our syllabus. The section is titled as the Superposition of Periodic Motions. So this is our new section which we have to discuss. Now, under this section, we will discuss superposed vibrations in one dimension. We have to discuss different topics under this heading. So let us start. As you can see, we have to combine vibrations in one dimension and see what happens. All of you know that many physical situations involve the simultaneous application of two or more harmonic vibrations to the same system. For example, a human eardrum is in general being subjected to a complicated combination of such vibrations, resulting in some overall pattern of its displacement as a function of time. Now we are going to consider some specific cases of this combination process, but in that combination process, we are making a very basic assumption. So what is that assumption which we are going to make in discussing the combination or superposition of vibrations in one dimension? The basic assumption which we are going to take is the resultant of two or more harmonic vibrations will be taken to be simply the sum of the individual vibrations. So this is our assumption. The resultant of two or more harmonic vibrations will be taken to be simply the sum of the individual vibrations. And this assumption is true When, let me write it another color. This assumption is true if displacement is strictly proportional to the force producing it. Displacement is strictly proportional to the force producing it. So when the force and displacement are proportional, this assumption is true. So we can add simply the vibrations to get the combined vibration. And when this simple addition holds true, the system is said to be linear. That means we are going to consider linear systems. So let us move to the first topic. Our first topic is, let me use this color, two superposed vibrations of equal frequency. Two superposed vibrations of equal frequency. So this is my first topic in the section which we have started, the superposition of periodic motions. And of course, we are doing the superposition in one dimension. In first case, we are taking vibrations of equal frequency. So let us start. Let me use this color. So suppose we have two simple harmonic motions described by the following equations. X1 equal to A1 cos omega t plus alpha 1. Second one, X2 equal to A2 cos omega t plus alpha 2. As you can see, these are two simple harmonic motions with different amplitudes. A1 is the amplitude of first SHM and A2 is the amplitude of second SHM, but the frequency is same. You have omega and omega in both equations, but they differ in phase because here phase constant is alpha 1 and in second case phase constant is alpha 2. So we want to combine them and see what is the nature of the resultant or combined motion. So their combination is then as follows. If x is the position function of the combined motion, x is x1 plus x2, as we have discussed our assumption that the resultant of two or more harmonic vibrations will be taken simply as the sum of individual vibrations, because we are discussing linear systems. So we add x1 and x2 to get the resultant motion. So x is x1 plus x2. X is our position function for the combined motion. So let us put for x1 and x2, x1 is a1 cos omega t plus alpha 1 plus a2 cos omega t plus alpha 2. a1 cos omega t plus alpha 1 plus a2 cos omega t plus alpha 2. So let me name it as equation first. So this is my equation first. We will justify that it is possible to express this resultant displacement x as a single harmonic vibration, as x is equal to a cos omega t plus alpha. Let me encircle it. We are claiming that this resultant displacement x can be put in this form, in simple harmonic form. That means we are saying that this combined motion is also a simple harmonic motion with certain amplitude a, with same frequency omega as the frequency of the individual motions, and with phase constant alpha. Now, what is our next purpose? We are claiming that we have claimed that it can be put in this form. That means we are saying that the resultant motion is also a simple harmonic motion with certain amplitude a, with same frequency omega, and certain phase constant. Now we have to justify it and see what is the relationship of a, that is the amplitude of the resultant motion, with the amplitudes of individual motions a1 and a2, and what about the relationship between the phase constant or phase of the combined motion with the phases of individual motions. So let us do that, and we will use the rotating vector description of SHM. So let us use the rotating vector description of SHM as it provides a very nice way of obtaining this result in geometrical terms. Which result? We will see how geometrically we can obtain that the combined motion is also a simple harmonic motion given by this particular equation using this rotating vector description of SHM, simple harmonic motion. So I will draw a figure first, then we will move. So let me draw the figure. This will be my origin. Use another color. This color. So let me name it. I will complete the figure first, then I will explain. Let me complete the second part of the figure. This color. Let me complete the figure. You can complete it with me. So this is part A, this is part B, and I name it figure 1. Let me check it. N1 and K. This is A, B1, P is A2. This is A1, this is beta. Okay, let us proceed. As we said that we will make use of rotating vector description of simple harmonic motion in order to get this result, that the combined motion, when we combine these two simple harmonic motions along one dimension having same frequency, the combined motion is also simple harmonic motion with some amplitude A and same angular frequency omega. So let us move to the figure. Now in figure 1a, as you can see, OP1 is a rotating vector of length A1. This length is, let me write it. OP1 is a rotating vector of length A1, making the angle omega t plus alpha 1 with the x-axis at time t. So OP1 vector is representing first SHM. Which SHM? The SHM given by, I name it first simple harmonic motion, this one, and I name this as second SHM. As you can see, the first SHM has amplitude A1, therefore the rotating vector which represents it must have length equal to its amplitude. So OP1 vector has length, this is A1. It is representing first SHM, it has length A1, and it is making angle omega t plus alpha 1 with x-axis at time t. So as it rotates in counterclockwise sense, its projection on x-axis, which is representing x, as you can see at this time t, its projection ON1 is just x, that will be A1 cos omega t plus alpha 1. As you know, in rotating vector representation of SHM, the projection of the rotating vector represents the position time function of SHM. So this ON1 is its projection at time t. As OP1 vector rotates, this ON1 length will change, and that will represent x1, which is just A1 cos omega t plus alpha 1. Right? Now you can understand OP2 vector has length A2. So what is now OP2 vector? Is the rotating vector of length A2 at the angle omega t plus alpha 2, right? So it is representing second SHM. This is representing second simple harmonic motion. As you can see, in second simple harmonic motion, amplitude is A2 and angle is omega t plus alpha 2. So OP2, this vector will have length A2 and it is making angle omega t plus alpha 2 with the x-axis at time t. So as time proceeds, this vector rotates in counterclockwise sense and its projection on x-axis, which is just x2, which will be A2 cos omega t plus alpha 2, changes, right, with time. So this angle is omega t plus alpha 2. Now the sum of these is then the vector OP. You can see simple vector addition rule, how we add two vectors. Now OP1 vector represents first SHM, OP2 vector represents second SHM. So to get the sum of these vectors, the resultant of these vectors, we completed the parallelogram OP1P2, and then this diagonal OP is the resultant of these two vectors, right? So let me write it. The sum of we write it neatly. The sum of these, that is OP1 and OP2, OP1 and OP2 is the vector OP as defined by the parallelogram law of vector addition, right? Let us move to the figure. This is OP1. Now, when you complete the parallelogram, remember the opposite sides of parallelogram are equal and parallel. So by equality of vectors, PP1 is the same vector as OP2. So OP2 and PP1 are equal vectors. So my resultant vector OP is representing the resultant SHM. I name it resultant SHM, right? So OP vector represents, let me use this color, resultant SHM. You can understand what should be its length. Its length should be A, and its angle with x-axis must be omega t plus alpha. You can see the length of this OP vector is A, and the angle made by it, let me show it in green. This angle is omega t plus alpha. It is shown in part B of the figure. This OP1, it has length A1, it makes angle omega t plus alpha 1 with x-axis. Now PP1 is same thing as OP2 by equality of the vectors, and OP has length A. So let us move. Now, as I have said, this is important, as OP1 and OP2 rotate at same angular speed omega, because frequency of both SHMs is same, so their vectors, the vectors representing these SHMs are moving at same rate. So we can think of this parallelogram OP1P P2 as a rigid figure that rotates bodily at this same speed. This is important. So let me write it. So let me write as OP1 and OP2 rotate at the same angular speed omega, we can think of the parallelogram OP1 P2 as a rigid figure that rotates bodily at this same speed omega. You can see OP1 rotates at same speed, angular speed omega as OP2. So this parallelogram, whole parallelogram OP1 PP2 will rotate bodily, that is as a whole parallelogram with the same angular speed omega. It will be rigid in rotation. It will not distort as the motion takes place, right? Now the vector OP can be obtained, as we have said, as the vector sum of OP1 and P1P, because P1P is equal to OP2. Now since we use another color, since angle N1 OP1 is equal to omega t plus alpha 1 and angle KP1P is equal to omega t plus alpha 2. Let me show you these two angles in the figure. N1 OP1, this one, N1 OP1, this angle, it is omega t plus alpha 1. Then KP1P angle, KP1P is this, KP1P is what? Omega KP1P is omega t plus alpha 2 kp1p is omega t plus alpha 2. Understand it. This angle is same as this angle. The angle made by OP2 with the x-axis is omega t plus alpha 2. That means angle KP1P is also omega t plus alpha 2. Why so? Because this whole thing is a parallelogram, OP1P, P2. P1P is parallel to OP2. So this angle made by OP2 with x-axis will be same as the angle made by PP1. If you produce this P1 or P1P to the x-axis, it will make here omega t plus alpha 2. Same will be this angle, right? So this is omega t plus alpha 1. And this is overall in this figure. We produce this. This overall angle is, let me show it, omega t plus alpha 2. So this angle, the angle between OP1 and PP1 is what? Alpha 2 minus alpha 1. The conclusion is the angle between, therefore, the angle between OP1 and P1P is just alpha 2 minus alpha 1. It is simple. I'm saying angle between OP1 and P1P is alpha 2 minus alpha 1. That is this angle, right? When you subtract this, this is whole angle is this, then P1P is shifted from OP1 by alpha 2 minus alpha 1 angle, right? It's easy. You can think about it and get it. Convince yourself. Hence we have A square is A1 square plus A2 square plus twice A1 A2 cos of alpha 2 minus alpha 1. Let me encircle it. A square is A1 square plus A2 square plus twice A1 A2 cos of alpha 2 minus alpha 1. This is simple result. Remember from your previous classes, you know, if I have a vector having length A and some other vector having length B, and if theta is the angle between the vectors, and I have the resultant of these vectors having length R, then there's a relationship that the length, square of the length of the resultant, that is R square, is equal to square of the length of one vector, that is A square, plus square of the length of another vector, that is B square, plus twice length of one vector, that is A, length of other vector, that is B, into cosine of the angle between the vectors. I repeat, if I have a vector of length A, then another vector of length B, and R is the resultant of the vectors having length R, and angle between the vectors A and B is theta, then R square is A square plus B square plus 2AB cos theta. We have just used this formula. Understand it from the figure. I have OP, it is a resultant of OP1 and P1 or P1P. P1P is representing second simple harmonic motion, its length is A2. OP1 is representing first simple harmonic motion, its length is A1. And OP is the resultant harmonic motion, its length is A. Angle between OP1 and P1P is alpha 2 minus alpha 1, as we have justified it right now. So A square is A1 square plus A2 square times twice A1 A2 cos of the angle, which is alpha 2 minus alpha 1. So we're here. A square is A1 square plus A2 square plus twice A1 A2 cos alpha 2 minus alpha 1. Now, the vector OP makes an angle beta as shown in figure 1b with the vector OP1 such that, use another color here, such that A sine beta is equal to A2 sine alpha 2 minus alpha 1. Let me encircle it. So I'm saying the vector OP makes an angle beta with the vector OP1 such that A sine beta is equal to A2 sine alpha 2 minus alpha 1. Let me show you the figure. 1b, you can see OP vector having length A is making angle beta with OP1. Now I'm saying that A sine beta is equal to A2 sine alpha 2 minus alpha 1. Where from it is obtained? Remember, there is a result called law of sines. What is the result? If I have a triangle, let the length of, let me use another color, let the length of this side be A and the opposite angle be alpha to this side, let the length of this side be P and the opposite angle be beta. Let the length of this third side be C and the opposite angle be gamma. So I have a triangle in general with three sides having lengths A, B, C. Angle opposite to side A is alpha, angle opposite to side B is beta, and angle opposite to side C is gamma. Then law of sine says sine alpha over A is equal to sine beta over B is equal to sine gamma over C. Understand it? Sine of this angle alpha over the length of the opposite side is equal to sine of angle beta over the length of the opposite side is equal to sine of gamma over the length of the opposite side. And you also know sine of 180 degree minus theta is equal to sine of theta. Sine of 180 minus theta is equal to sine of theta. So let us use this to understand how A sine beta is A2 sine of alpha 2 minus alpha 1. Let's move to this figure. Now, this angle here is alpha 2 minus alpha 1. Now, which two lengths are in our equation? A and A2. A and A2. So we're concerned with this and this side, right? So sine of beta in this triangle OPP1, sine of beta, let me move to the equation, sine of beta over A2 sine of beta, let me write it here, sine of angle beta over the length of the opposite side is A2 must be equal to, which is the side, sine of, let me move to the equation, I have sine of alpha 2 minus alpha 1. Now understand it, when I produce this whole angle is 180 degrees. If I produce OP1 like this whole angle is 180 degrees. Therefore, this angle, let me use another color. I think this color or other color, yellow one. So this angle is what? This is 180 degree minus alpha 2 minus alpha 1, right? This whole angle, let me use again red, this whole angle is 180 degree. This much is alpha 2 minus alpha 1. So this orange one is 180 degree minus alpha 2 minus alpha 1. So I can write sine of, using law of sines, 180 degree minus alpha 2 minus alpha 1, which is this internal angle, over A. Sine of beta, this angle, over the length of the opposite side, which is A2, is equal to sine of this angle, 180 degree minus alpha 2 minus alpha 1, over the opposite length of the opposite side, which is A. Now, another thing, as we said, sine of 180 minus theta is sine theta. So this is, let me use another color. This is equal to sine of alpha 2 minus alpha 1. Sine of 180 degree minus theta is sine theta. Our theta is alpha 2 minus alpha 1 over A. That's why we have written that A times sine beta is equal to A2 times sine alpha 2 minus alpha 1. So think about it. Convince yourself. This is not difficult. So we are here. And the phase constant alpha alpha of the combined vibration is given by alpha is alpha 1 plus beta. It's easy. Let me use red color. I'm saying the phase constant alpha of the combined vibration is given by alpha is equal to alpha 1 plus beta. Check it yourself. This is easy. Remember, alpha is the phase constant of the combined or resultant SHM. This one. So we have obtained certain results geometrically. So we have said or justified that if we have one simple harmonic motion given by this and another simple harmonic motion given by this, and we combine them, we will get the simple harmonic motion, resultant simple harmonic motion, whose amplitude is related to individual amplitudes through this equation, and the phase relationship among these motions is embodied in this equation and this equation, right? We can use complex exponential formalism, which can take us directly to the same results. So let us use. Let me use another color. Now, using complex exponential formalism, we use the complex exponential formalism. We will see that we get the same results. So let us do the rotating vectors OP1 and OP2 are described by the following equations. Z1 is equal to A1 e raised power j omega t plus alpha 1. Remember how we express where representing now OP vector by complex number Z1. A1 is its length, and we know omega t plus alpha 1 is the angle made by OP1 with the x-axis. You know it. We have already discussed it in the previous lectures. What is the vector representation of complex numbers? And Z2 represents OP2. It will be written as A2 because A2 is the length of OP2. E raised power j times omega t plus alpha 2. Remember, j is just square root of -1. You know that. Sometimes we write it by iota, but in physics we write it by j, represents square root of -1 by j, because I is the reservoir for electric current. So Z1 is A1 e raised power j omega t plus alpha 1. Z2 is A2 e raised power j omega t plus alpha 2. So this is my first SHM using complex exponential formalism. This is my second SHM. So what will be my resultant? So hence, let me use another color here. I think this one. Hence, the resultant is given by, remember we are using describing linear systems. So Z is just Z1 plus Z2, which is just A1 e raised power j omega t plus alpha 1 plus A2 e raised power j omega t plus alpha 2. So this Z is my combined or resultant simple harmonic motion. So Z is Z1 plus Z2, which is A1 e raised power j omega t plus alpha 1 plus A2 e raised power j omega t plus alpha 2. Now we can write it as, we can rewrite Z as Z is equal to e raised power j omega t plus alpha 1 times A1 plus A2 e raised power j alpha 2 minus alpha 1. Let me encircle it. Z is e raised power j omega t plus alpha 1 times A1 plus A2 times e raised power j alpha 2 minus alpha 1. Let me name it equation second. This was my first. So you can see I have factored out e raised power j omega t plus alpha 1 from this z equal to z1 plus z2. So I obtain this thing. Check it, it is easy. Check it at home. Now remember, we have discussed in discussing complex numbers, e raised power j theta is just an instruction to apply a positive rotation through the angle theta, right? So I'm claiming that the combination of terms, right? Let me write it, then we will discuss. So the combination of terms in square brackets of equation 2 specifies that a vector of length a2 is to be added at an angle alpha 2 minus alpha 1 to a vector of length a1 and write it as a color, and the initial factor exponential of j omega t plus alpha 1 tells us that this whole diagram is to be turned to the orientation shown in figure 1b. Let me check it, then I will. I said ej theta is just an instruction to apply a positive rotation through the angle theta. So the combination of terms in square brackets specifies that a vector of length a2 is to be added at an angle alpha 2 minus alpha 1 to a vector of length A1 and the initial factor exponential j omega t plus alpha 1 tells us that this whole diagram is to be turned to the orientation shown in figure 1b. So let me justify it. In last lecture, we said if we have some complex number represented by certain vector, and we multiply that complex number with ej theta, so the new complex number will be a vector rotated through angle theta in counterclockwise sense related to previous vector z. I again repeat it. I said if I have some complex number represented by some vector, now I multiply ej theta to z. This new complex number will be a vector having same length as z. This is my ej, let me write it neatly, e raised power j theta z, but it will be rotated through angle theta in counterclockwise sense, right? So let us move. So the thing in this square bracket is what? So first we have a vector. I'm saying that it tells us it's a vector which we obtain how? We have to add a vector of length a2 at an angle alpha 2 minus alpha 1 to a vector of length a1. So I have a vector of length a1, understand it. I add to it a vector of length a2 at an angle alpha 2 minus alpha 1. A2 is to be added at an angle alpha 2 minus alpha 1 to a vector of length a1. So this is my a1. I add to it vector of length a2 at an angle alpha 2 minus alpha 1. This is the thing in square brackets of equation 2. I have a vector of length a1, then I add to it a vector of length a2 at an angle alpha 2 minus alpha 1. So this is mathematically my square brackets of equation 2. Now, then this factor is multiplied to it, e raised power j omega t plus alpha 1. That means what? That means that this whole combination of two vectors is to be rotated in counterclockwise sense, which we call positive rotation, through an angle omega t plus alpha 1. So this whole arrangement is to be rotated through angle omega t plus alpha 1, because here it is e exponential j omega t plus alpha 1. When you do that, what will happen? When you rotate this whole thing, this will look like the diagram of figure 1b. So I had first vector of length a1, then I add to it vector of length a2 at an angle alpha 2 minus alpha 1, then I rotate this whole picture through angle omega t plus alpha 1. So I obtain this. So OP is my resultant So you can see the advantage of using this complex exponential form, this interpreting this equation of Z, you obtained the geometrical interpretation. So the resultant Z vector will be obtained by rotating this whole thing. That means resultant Z is this vector OP. Right? Think about it and convince yourself. So we have justified two ways. First, we use the rotating vector description of SHM to establish that if we have two SHMs of equal frequency given by x1 and x2, then the combined motion is also SHM. It has the amplitude A and same angular frequency omega, and A and A1's A1, A2 are related by these equations. Then we did the same thing using complex exponential formalism. Let me move to the last piece of this lecture. Now, in general, we talk now in general terms, the values of A, that is the amplitude of the combined SHM, and alpha, that is the phase constant of the combined or resultant vibration, for the resultant disturbance cannot be further simplified. So I'm saying that in general, this A, which we obtained in terms of A1 and A2 and alpha, which had this relation alpha equal to alpha 1 plus beta, cannot be further simplified than that we obtained. But the special case in which the combining amplitudes are equal is noteworthy. So in general, you cannot simplify it further. But if the amplitudes of the two combining SHMs are equal, that case is to be worth noting. So if we denote the phase difference to see alpha to alpha 1 minus alpha 1 is just phase difference. Justify it. This is the phase of first SHM, this is the phase of second SHM. If you subtract them, omega t will go, you'll get alpha 2 minus alpha 1. So alpha 2 minus alpha 1 is just phase difference between combining SHMs. So for this simple case in which the combining amplitudes are equal, we represent this phase difference between the combining vibrations as delta. So delta is our phase difference. Then from the geometry of the vector triangle in figure 1b, let me write it first, then I will justify. One can write the following results just by inspection the triangle. Beta is delta by 2 and A is twice A1 cos beta, which can be written as twice A1 cos delta by 2. Let me encircle it, then I will. Beta is, let me name it third. Beta is delta by 2. A is twice A1 cos beta, is twice A1 cos delta by 2. So let us move to understand it. Where is our figure 1b? This is our figure 1b. See, now I have this triangle OP1 and another triangle OP. Now I'm saying if their amplitudes are equal, then let me draw a small angle. So if this is my triangle, sorry, if this is my OP1, then I have OP, and this is my, let me use some other color. This is my OP, right? This is my phase difference, alpha 2 minus alpha 1. Now I'm saying let the two amplitudes of the combining oscillations be equal. So now A1 and A2, this is A and this is beta. So I'm saying A1 is now A2, right? So what will happen in that case? I'm saying that we will have beta equal to delta by 2. So this is my delta. Alpha 2 minus alpha 2, alpha 1 is our delta. This is my delta, right? This is my delta. Alpha 2 minus alpha 1 is my delta. Let us move to the figure now. How beta is delta by 2. This delta, if this is beta, then this is also beta. Why? Now this is also beta. Why so? Angle is opposite to equal sides are equal. Because A1 and A2 are equal sides, this angle is the angle opposite to A1. Beta is the angle opposite to A2, these sides are equal, then this is also beta, right? This is beta, this is beta. Now there is a result that exterior angle of a triangle is equal to sum of interior opposite angles. So now this beta and beta are two interior opposite angles of this triangle, and delta is exterior angle. So delta is beta plus beta. I repeat, exterior angle of a triangle, which is delta, is equal to sum of interior opposite angles, which is beta plus beta. That means delta is 2 beta. So beta is half delta. Beta is half delta. So we have justified it. Now let us move to the formula in which, remember, we said A square is A1 square plus A2 square plus twice A1 A2 cos alpha 2 minus alpha 1. This formula. A square is A1 square plus A2 square plus twice A1 A2 cos alpha 2 minus alpha 1. Now A1 is A2. Let me use this color. When A1 is A2, then A is given twice A1 square. I replace A2 by A1. It will become A1 square plus A1 square, that is twice A1 square, plus twice again A1 square. A2 is A1. So it will twice A1 square times cos of this is our phase difference, which we have designated by delta. It's cos of delta, right? So you can take twice A1 square common. It will become twice A1 square into 1 plus cos of delta. So A square is twice A1 square times 1 plus cos delta. Then you can see to obtain A is twice A1 cos beta. Beta is just delta plus, let me check it. There's A1 square plus A2 square. It becomes A1 square plus A1 square, twice A1 square plus twice A1 square. Cos of this I take twice A1 square common. It will become 1 plus cos delta. Then you take the square root. Is it 2? Let me check it. Twice A1 cos beta is twice A1. Check it. A square is A1 square plus A2 square. It's twice A1 A2 cos alpha 2 minus alpha 1. Alpha 2 minus alpha 1 is delta. That's my delta. I'm missing something. It's twice A1 square, 1 plus cos delta. Then I can write it. When you take the square root, what will it become? You check it. Now twice A1, A2 cos alpha 2 minus alpha 1. I simplify it to this point, then you do it yourself. I'm not, I simplify it to this point, twice A1 square into 1 plus cos delta is it is cos delta. Okay, I can write it cos beta twice beta. It is when I replace delta, it is cos twice beta. You have to use now a trigonometric identity. It's okay. Twice A1 square. First I do it twice A1 square. Then I do it twice A1 square cos. I replace alpha 2 minus alpha 1 by delta. Delta can be written as twice beta. Then you use a trigonometric identity to obtain this, right? So check it at home. This can be done, this is easy. You have to use the formula of cos 2 theta. You will reach here, right? Then this is the end of the lecture. So let me summarize today's lecture. So today we started another section of our syllabus, the superposition of periodic motions. Under this section, we discussed superposed vibrations in one dimension. We said there are systems which oscillate under the action of combined vibrations. We gave the example of eardrum, and we said in doing so, we will assume the system to be linear. That is, the resultant of two or more harmonic vibrations will be taken to be simply the sum of the individual vibrations. And we said that assumption is true when the displacement is proportional to the force producing it. Then we discuss the superposition of two SHM'S with equal frequency. Amplitudes were different, there was phase difference, and we justified this is also a simple harmonic motion with certain amplitude and same frequency and certain phase constant. Then we related through rotating vector representation the combined amplitude with the individual amplitudes and justified the phase relationship between the combined motion and the combining motions. Then we did the same thing using complex exponential formalism. Then we at the last said that we cannot simplify it further, but in the special case of equal amplitudes case, we said we can write beta as delta by 2, where delta is phase difference, and A can be written as twice A1 cos beta. Now I gave you some homework throughout the lecture. First homework was first homework. This homework was first you have to convince yourself throughout the lecture. Here I told you check it yourself, it's easy. Then here I told you check it at home, it's also easy. And convince yourself this argument which we said about interpreting this equation 2, which was a complex version of our resultant SHM. Then at last I told you to check it. at home that we really obtain from this now, from this onwards, this using a suitable trigonometric identity. So this all for today. Go through all the lectures, don't waste your time, prepare your exams, and don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.